Hi all, welcome to my ozone technology course. This will be session 25B, the ozone in cooling towers. The topics that I will be discussing in this session will include the capital cost for the ozone installation in cooling towers, the total operating cost per annum using ozone, typical operating parameters with ozone, the quality of water in the cooling tower basin, and the chiller tubes before and after the ozone application. You will note that in chemical treatment, the only capital costs will be the dosing pumps and a tank to keep or store the chemicals. But in ozone systems, the capital cost becomes significant. First, the capital cost will have to include an ozone generator, the ongoing, we need a secondary pump, a compressor if it is not available within the system. Generally, most large cooling tower system will have a compressor. The operation is 24/7. There's a control panel. If it is not in the ozone generator, it should be separate. The cost is for general plumbing and electrical, and the total power requirement for application of ozone will not exceed 500 watts per day. Corrosion inhibitors may be recommended or optional in order to reduce the electrolytic corrosion that cannot be prevented by any other chemicals. This table represents the real time operation cost for chemical as well as per ozone on the same towers. The source is given in the reference at the end of the presentation. If you look at the cost, you'll find when you use chemicals, there's not much of a cost, electrical cost, other than the dosing pumps, which are very small costs. The chemical cost per month, per year is 18,613. It's almost $1,000 per month, or $1,500 a month. Of course, this particular cost structure is stated at 1995. So you have not, for the current cost of chemicals, would probably far exceed this amount. The labor cost for chemicals treatment will be about $9,000 a year. Again, in 2021, it should be maybe double or triple. Whereas your labor cost for chemicals, it's only about $2,800 a month compared to that of the chemical, which is approximately 1/4. The water usage with chemicals will be around $43,000, and if ozone is used, it's only $4,000. This is only mostly top up, and the expenditure for chemicals is because there's a heavy blowdown to reduce the TDS, loss of chemicals, and we have to top up against that water loss. Then you have the chlorine gas. you use biocide as chlorine. That is $6,000 a year. But if you notice that these chemicals are different from chlorine, so if you really add them up together, it's about $24,000 a year on chemicals. And if chlorine is not used, obviously this will be substituted by chemicals, which will be no less. The power consumption, if you notice through chemicals, there is $118,715 for the whole air conditioning system. Whereas if you use ozone, it comes up to $47,000. If you notice that it is about 1/3. So you will probably save 2/3 of your power consumption if you use ozone. So total for the year, it's 198,000 versus 57,000, which is around 1/4. So you will notice that by using ozone, you will have significant cost savings in water, labor, electricity. Now we have to accept the fact that the cost of ozone generation system has dropped tremendously because of improved technology, and therefore application of ozone systems in cooling towers in the 2021 is even far more attractive than 1995 given here. This chart shows the history of ozone treatment system VB cooling tower at Kennedy Space Center. Just to let you know, the previous charts table which I gave you has been obtained. The information has been obtained from this application. They have, in their testing, they did 4 phases. Between 94 and 96, they used the first generation air fed. They got a ozone yield of 75 to 1.5. In phase 2, they had in 1996-1997, they were able to increase the dosage or production capacity 3 grams per 100 tons rather than 2 grams per hour per 100 tons, and the yield was about 0.75 to 1.5. And the second generation improvement gave more, and the second generation oxygen feed gave up to 20 grams an hour. So the difference between an air fed and oxygen fed, same systems, can have a much difference, and you get much more ozone coming out. This is a chart or table for the data application in the Kennedy Space Center on the ozone treatment of the cooling towers. They had a flow rate of gallons per minute of 1,000 or 200 SCFH. They've given a pipe diameter of 5.7 inches. Concentration of feet per percentage by weight was 6%. Pipe length was 300 feet. Velocity flow rate, that is 13.2 flow rate. Reynolds number, this is to do with turbulence and fixing, etc., is 575 to 475. Contact time, they had about 10 seconds for the ozone to contact with the water. The pressure is 100 per 100 feet is 4 psi, and ozone ppm was delivered only as 1.5, 1.7 ppm. So 1.7 ppm is very low amount of ozone we are producing, we are applying, and we would be able to get a very good ozone treatment in smaller towers with ozone producing at about 2 to 5 grams per hour. The corrosion tests were done in this test national laboratory on 2 case studies in 1995. The iron showed 2 mils per hour per year of corrosion and 0.37 mils per year of pitting. It was reported that the corrosion effect of ozone was 50% of that of chlorine treatment. So this is a comparison of chlorine against ozone. The table here is chlorine, against biocides with ozone. The total bacteria was above 100,000 CFU per mil. With ozone, it will show below 100 CFU per mil. Legionnaire will be below 10 CFU. Dissolved iron will be below 1 ppm and is removed by ozone. Copper corrosion rate is below 0.005 millimeter per year. The steady state corrosion is 0.005 millimeter, below 0.005 millimeter per year. Mild scale corrosion is below 0.15 millimeter per year. TDS was below 1200. Cycles of concentration depends on TDS of the raw water. Soft water was below 50 ppm in this case, which means the cycle will be approximately 25. So you can go up to 25 cycles. The water about 100 ppm. Hard water was 400 ppm. So if the water is 100 ppm, then the cycles will be 12. If the hard water is 400 ppm, the cycles will be 3. So if you notice that the harder the feed water, the lower the cycles you're going to have. This photograph shows a typical difference between the quality of water in the ozone treated tower as against that in the chemical treated tower. If you notice, you will get, if you use ozone to treat your towers, you will get water of this clarity and quality. Whereas if you use chemicals, this will be the color and quality of the water you will get. However, please note this color is quite extreme because it has quite a bit of tannin and some rust involved, so that gives you the darker color. Usually it will be a light coffee color or tea color, straw tea color. This slide has represents a picture of the condenser after the chiller plates have been removed. This is the chiller plate, this is the condenser. These two pictures are from chemical treatment. When the chiller plate is opened, you will see deposits of scaling, rusting, and clogging of all the holes in the copper tube. During servicing, all this has to be scrubbed clean, and it will be necessary sometimes to put into the tubes wire brushes or copper rods or iron rods, to remove the scaling. This picture at the bottom shows the amount of rust and scale that has built up, and this half is after it has been cleaned up. Now, this picture, for those who want to know more about the heat exchanger or chiller tubes, which we call, and the flow pattern of the chiller water and the refrigerant. The refrigerant goes in and goes through, wanders up and down interrupted by the baffles. This ensures that the water flow is reduced so that there's more contact time within the copper tubes. The chilled water flows into one side of the condenser and moves in one half, flows through and returns through the other half and flows upwards. So there is a small barricade here to prevent water shunting. So all the water must go through the chiller tubes and out of the other section of the chiller tubes and flows out. This makes sure there is a good transfer of heat from the refrigerant to the chiller or cooling tower water. This picture shows an ozone treated tower. A picture was taken before the installation, after it is completely been cleaned up, and 1 year later the chiller tubes were opened up, and this is what appeared. You will see, in fact, the best we cleaned before, but once ozone has been applied, the chiller tubes have become cleaner than even our original clean chiller tubes. So you will note that ozone is a very efficient cleaning agent, ensures there is no scaling, ensures there is no rust, ensures the workload for you to clean the chiller tubes every year is very, very low, and you save a lot of time. Also, like in Australia, there's a statutory requirement that you have to clean the towers every 6 months, but if you apply ozone, you can do that in once a year. So you do save time in labor, save time in chemicals, and save time in downtime, because cleaning up a chemical treated tower will take twice or 3 times longer than cleaning up an ozone treated tower. This is the end of session 25. Thank you for all who has the perseverance to listen to my session. The next session 25C will be on the principles of application of ozone to cooling towers on the third part. If you are new to this session, please refer to sessions 1 and 2 on the program details and sessions 3 to 25B for the full presentations. If you like this presentation, please click the like icon and subscribe icon if you want to be notified of the next session. Thank you and have a good day.